Picture a long line at a ticket counter. The people don't stand in one tidy block. They're scattered around the room. The clerk only needs to know one thing. Who comes next? A linked list stores data exactly like that. Instead of one solid block of memory, we scatter little nodes wherever there's room, and each node simply remembers who follows it. An arrow pointing to the next one. That one design choice. Follow the arrows instead of counting a fixed distance. Flips the whole cost story. Arrays are fast to index, but slow to reshuffle. Linked lists are the mirror image. Let's build one and see exactly why. Here is a single node, up close. It has just two compartments. The left cell holds the value. Here, 10. The right cell holds a pointer, a stored memory address that says where the next node leaves. Think of it as an arrow waiting to be aimed. Now let's chain a few together. We always keep one special pointer called head. It marks the very first node. Place the first node, holding 10, and point head at it. Add a second node, 20. Aim the first node's next arrow straight at it. Then a third, 30. And again, wire the previous arrow across. The last node has nobody after it, so its next points to null, nothing. We draw that as a little ground symbol. That null is how you know you've reached the end. And that's a complete linked list. 10, arrow, 20, arrow, 30, arrow, null. Head at the front, the trail of arrows defining the order. How do you read a linked list? You can't just jump to the third element the way you would in an array. There's no address formula here, only arrows. So we walk. Start a second pointer, current, at head. Read its value, 10, and print it. Follow the arrow to the next node. Current is now 20. Print 20. Follow the arrow once more. Current is 30. Print 30. Follow the last arrow and current lands on null. That's the stop signal. The walk is over. To reach the kth node, we took k hops. So in the worst case, reading a linked list is order n. Linear, not instant. Compare that to an array, where element k sits at the start address plus k times the element size. One calculation, and you're there. That's the array's superpower. Constant time indexing. A linked list simply can't do it. Now the operation linked lists are built for inserting. Here's a list, 20 then 10 with head on the 20. Let's push a new node, 30, in at the front. Create the new node holding 30. It's floating free right now. Its next point's nowhere yet. Here's the rule that saves you. Point the new node forward first. Set its next to the current head, the 20. Do this step before anything else, or you lose the rest of the list. Only now move head to the new node. 30 becomes the first node. Its arrow already locked onto 20. Two-pointer changes, and it's done. Notice what we did not do. We never touched the other nodes. No shifting, no copying. Insert at head is constant time. Order 1, no matter how long the list is. The other case, insert after a node you already hold. Say we have a pointer p sitting on the 30, and we want a new node, 25, right after it. Make the new node. Then two arrows do everything. First, new nodes next equals ps next. So 25 points to 20. Second, ps next now equals the new node. So 30 points to 25. We bend the old arrow from 30 up to the newcomer. Read the chain now. 30, 25, 20, 10. The new node slid in with just two pointer edits. Order 1, given the node. That order matters. Aim the newcomer forward before you redirect P, or you'd snap the link to the rest of the list. Deletion is the same idea in reverse. You make an arrow skip over a node. Here's 5, 12, 7, 9. Let's delete the 12. To unlink a node in a singly linked list, you need its predecessor, the node whose arrow points at it. Here, prev is the 5. The target is the 12. The trick is to redirect prev's arrow past the target. Set prevs next to the targets next. In other words, make 5 points straight to 7, leaping right over 12. Watch the arrow bend across. The 12 is now unreachable. No arrow points to it anymore, so it just floats away, and its memory is reclaimed. The list reads 5, 7, 9. Done. The rewire itself is a single pointer change, order 1. But finding the predecessor from head cost a walk. So deleting by value is a walk to find, order n, plus a splice, order 1, overall order n. Hold the node and its prev, and only the order 1 splice remains. One quick upgrade first. Everything so far was singly linked. Arrows point only forward. A doubly linked list adds a second pointer in each node. Prev, pointing backward. Now every neighbor is joined both ways. With a backward arrow, you can walk the list in reverse. And crucially, given just a node, you can find its predecessor instantly. So you can delete it in constant time with no walk at all. Now the comparison that ties it all together. Line the two structures up on the operations that matter most. Access the kth element. The array wins big, constant time by address. Against the linked lists, linear walk. Search by value is a tie, with no sorting or hashing. Both scan from the start. Order n either way. But insert or delete at a spot you already hold flips it completely. The array must shift every element after the gap. Order n. The linked list just rewires a couple of arrows. Order 1. That is the linked list's whole reason to exist. There's a price for all that flexibility. Every node carries an extra pointer, so it uses more memory, and the nodes are scattered instead of packed, which is unfriendly to the cache. Arrays stay contiguous and fast to scan. It's always a trade. Let's put it together on one list. 30, 25, 20, 10. The task, insert 15 after the node holding 20, but we're given only head. So we split the job into find, then splice, find phase. Walk from head, comparing each value to 20. Start at head. 30? No. Hop to 25. Not it. Hop again. 20. Found it. Call this node P. Splice phase. New node 15. Point it forward first. Its next equals PS next. So 15 points to 10. Then redirect P. 20's next now points down to 15. The final list reads 30, 25, 20, 15, 10. Finding was order n. The splice was order 1. Your turn. Here's the list. 10, 20, 30. Insert a new node, 15, right after the node holding 10. Pause now. Wire the two arrows in the correct order and draw what you get. I'll wait. Here's the walkthrough. The node holding 10 is P. We already have it, so there's no walk. This is pure splicing. Step 1. Forward first. 15's next equals PS next. So 15 points to 20. Step 2. PS next equals the new node. So 10 now points down to 15. And there it is. 10, 15, 20, 30. If you wired those two arrows that way around, you've got it exactly. Trap 1. The big one. Rewire in the wrong order and you lose the list. Always aim the new node forward first. Then move head or P. Move head first, and the only link to the rest of the list is gone. Orphaned. Trap 2. Confusing position with a pointer. Insert after node P, where P is handed to you, is order 1. But insert at the kth position means walking from head to reach it first. That's order n. Trap 3. In a singly linked list, you cannot delete a node given only the node. You need its predecessor to rewire. Without prev, you walk from head to find it. Order n. A doubly linked list escapes this. And trap 4. Lists don't always win. Plain search by value is order n in both. And if you mostly index by position, an array's constant time access and packed, cache-friendly memory can leave a linked list behind. Let's lock it in. A node is data plus a next pointer. Nodes scatter through memory, head marks the first, and the last node's next is null. The one habit that makes linked lists predictable. Separate find from splice. Walking to a position or a value is order n. Rewiring the arrows, once you're there, is order 1. So insert or delete at a node you already hold with its prev in a singly list is constant time. Just bend a couple of arrows. No shifting a whole array, and the trade in one line. Arrays give you instant indexing but slow middle edits. Linked lists give you slow indexing but instant edits at a known spot. Pick the structure that fits how you'll use it, and the rest follows.